Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce Aditya Parmeswaran, who's been a former intern with us from Stanford University, to come here for a talk. Aditya has a lot of publications in databases. His DVLP count is more than 25, I think, actually. Some pretty large number. And sorry? A crowd of publications.
You know my secret.
And in fact, 2 of his papers have been among the best papers of the respective conferences. So he has a very distinguished record for a graduating PhD student, and he's here to tell us about human-powered data management. So, on to you.
All right. Thank you, Raghav, and thank you for inviting me. It's a pleasure to be here. Pleasure to be back, actually. All right. So I'm Aditya Parmeswaran from Stanford University. I'm going to be talking about human-powered data management. Right? So we are now in the midst of the big data age. Every minute we have 48 hours of video uploaded on YouTube, 100,000 tweets, and so on. Understanding this data would help us power a whole range of data-driven applications. Unfortunately, an estimated 80% of this data is unstructured. So it is images, videos, and text. Fully automated processing of unstructured data is not yet a solved problem. Humans, on the other hand, are very good at understanding unstructured data. They are very good at understanding abstract concepts. They are very good at understanding images, videos, and text. So incorporating humans doing small tasks into computation can significantly improve gathering, processing, and understanding of data. So the question is, how do we combine human and traditional computation for data-driven applications? So let me illustrate the challenges using a simple example. This is a task that I actually wanted to do for this presentation. So I want 5 clip art images of a student studying, of college age. There must not be a watermark, and it must be suitable for a presentation. Okay? So it's a simple enough task. So the first option is I do it myself, right? So, but this could take very long. I need to figure out which queries to issue to Google or Bing Images. Faux pas right at the start. So I need to figure out which queries to issue to Bing Images, and for each of those queries I need to go through hundreds and hundreds of results. So it's really painful. The second option is I ask a friend. Once again, it could take very long. The person might not do a good job, right? The third option is to orchestrate many humans. By orchestrating many humans, I could get results faster because I'm parallelizing. And because I'm using many humans, I may have low error. All right? Of course, orchestrating many humans gives rise to many different challenges. First, how should this task be broken up? Presumably, I need to gather images from an image search engine. Which queries should I issue? How many images should I gather? How should I check if these images obey properties? Right? To guarantee correctness, I may want to check one property at a time. In what order should I check these properties? Since humans make mistakes, I may want to ask multiple humans. How many humans should I ask? How do I rank these images? How do I optimize the workflow? How do I guarantee correctness? So these are the kinds of challenges that one needs to grapple with when orchestrating humans for human-powered data management. All right? So these challenges boil down to a fundamental 3-way trade-off that holds in this scenario. Trade-off between latency, how long can I wait? Cost, how much am I willing to pay? And quality, what is my desired quality? So recall that in traditional database query optimization, the focus is on latency. In traditional parallel computation, the focus is on latency and cost. And traditional uncertain databases, the focus is on latency and quality. In this case, we have a 3-way trade-off. So if there's one thing I'd like you to take away from this talk, it's our focus on this 3-way trade-off that permeates all of my research on human-powered data management. Right? So to get access to humans, we need to crowdsource. All right? So here is a diagram of the landscape of crowdsourcing in the industry by an organization called crowdsourcing.org. As you can see, it's a very active area. Each of these tiny icons refers to a separate company. Crowdsourcing means a lot of different things to different people. It could mean generating funding using the crowd, generating designs using the crowd, solving really hard problems using the crowd, and so on. in my work, I focused on crowd labor or paid crowdsourcing. To get access to crowd labor or paid crowdsourcing, one uses marketplaces. So all of the icons in this figure refers to a marketplace. Marketplaces allow users to post tasks via low-level API calls. People who are online can pick up these tasks and solve them. And the canonical example of a marketplace, which I'm sure a lot of you have heard of, is Amazon's Mechanical Turk. These marketplaces are growing rapidly. The size quadrupled in 2010 and 2011, and the total revenue reached $400 million in 2011. So here's an example of a task that I could post to one of these marketplaces, asking people, is this an image of a student studying? People who are online can pick up this task and solve it, and will get the 5-cent reward in this case. All right? OK, so now let me draw a diagram of the landscape of research in crowd labor or paid crowdsourcing and tell you how my work fits in. So there are lots of humans. There are lots of marketplaces, like I described earlier, to reach humans. And once again, the canonical example of a marketplace is Mechanical Turk. Then there has been work on platforms, making it easier to post tasks to these marketplaces, dealing with issues like how should you interact with humans, what kind of human issues arise, what kind of interfaces should one use, and so on. Then there is work on algorithms that leverage these platforms, having humans do the unit data processing operations like comparisons, filtering, ranking, rating, and so on. Then there are systems that call these algorithms, asking these algorithms to sort, cluster, and clean data. Of course, these systems can also directly leverage the platforms by having humans get or verify data. My focus has been on designing algorithms and systems. Right? So the focus of my thesis has been on designing algorithms and systems, and efficient algorithms and systems for human-powered data management. There are 4 aspects that I've studied: data processing, data gathering, data extraction, and data quality. I've also worked on other research that doesn't fit under the umbrella of human-powered data management. If there's time, I'll tell you about that towards the end of the talk. All right, so here's the outline of the rest of the talk. I'm going to tell you about 2 human-powered systems or applications that both motivate and are influenced by my research. I'll tell you about one of them immediately, and the other one interspersed with the second topic, which is filtering. Right? Filtering is a critical data processing algorithm that applies to both of the systems that I will talk about. I'll tell you about the other research I've done in crowdsourcing and in other topics, and then conclude with future research or open problems. All right, so the first application or system that I'm going to be talking about is the DataSift Toolkit. So the DataSift Toolkit is a toolkit for efficiently executing a specific kind of query, the gather, filter, rank query on any corpus. So the idea is you gather items from the corpus, you filter them, you rank them, and then you produce the result. And humans may be involved in all 3 steps: the gather step, the filter step, as well as the rank step. And what we've built is a general purpose toolkit that can be efficiently deployed on any corpus. Right? So let me dive into a quick demo. So a user of DataSift will see a screen like this. They'll select what they're looking for. In this case, Google Images. Sorry, I don't have one for Bing Images. But they'll select the corpus that they're looking for, type in what they're interested in, the conditions the items must satisfy. These are filtering predicates, and how the items must be ranked. So this is a ranking predicate. They can also specify how many results they want and how much they are willing to spend. All right? Now I'm going to play a video of how I would use DataSift to ask my query. So currently, DataSift is implemented over 4 corpora: Google Images, YouTube, Amazon products, and Shutterstock, but it could be over any corpus. For my clip art of student studying example, I would type in, give me a clip art of student studying, must be 1 student of college age, and so on and so forth. Right? Unlike a traditional search engine, notice that I can use as many words as I want to describe each of these predicates. Let's say I want 10 results, and I say that my budget is, let's say, $5. Okay? So this is how a user would post a query to DataSift. DataSift will translate this specification into questions that are asked to the crowd. So there are 3 steps: the gather, filter, and rank step. So it will actually gather items, in this case images, by issuing keyword search queries to the corpus, in this case Google Images. So in this case, it'll gather items by issuing the keyword search query, clipart of student studying. So the crowd is not involved in this gather step. But the crowd could also be involved in the gather step, and I'll show you an example of that next. Then DataSift checks if the images retrieved actually obey the filters using humans. Then DataSift ranks the items using humans, and then presents the results to the user. Right? Now I'm going to show you results from previous runs for this query. So this is one such result. This is just a portion of the result. There are lots more below. So the first column here refers to the rank given by DataSift for this query. The second column refers to the rank given by Google for this query for clipart of student studying. Okay, as you can see, the first 4 results are all fairly good. This is one student of college age, sitting with books, there is no watermark, and so on. Another interesting thing to note is that the item with rank 4 was actually ranked 78th in Google, so DataSift managed to pull it up. Now I'm going to play a video of me scrolling down so that we can look at the rest of the results. Okay, so then you have items with DataSift rank 5, 6, and 7, which are also fairly good. Then you get to items with DataSift rank -1. So these were items that DataSift discarded during processing because it felt that it did not satisfy one or more of the filtering predicates. These items were fairly high up in the Google search results for clipart of student studying, right? So they were ranked 3 all the way till 16. If you go and manually inspect each of these images, you'll indeed find that they do not satisfy one or more of the filtering predicates. The typical one that is not satisfied is the no watermark restriction, and sometimes it's not even clipart of student studying. Right, so the results are fairly good for this example. Now let me try to give you an even more compelling example. All right. So in this case, I'm looking for a type of a cable that connects to a socket that I took a photo of. So notice that I can add a photo as part of my query. And in this case, I'm searching over the Amazon products catalog. All right? So in this case, DataSift does not even, yes?
Sorry, just to understand, how would that photo be leveraged during the gather phase, right?
I'm getting to that.
Good.
Yeah. So in this case, DataSift does not even know what keyword queries to issue to the Amazon products corpus, as you rightly pointed out. So it asks the crowd for keyword query suggestions in the gather step. Right? And then it retrieves items corresponding to those keyword query suggestions, all in the gather step. Then in the filter step, for those items retrieved, it checks whether it satisfies this query or not. Right? So the items, and there is no rank step in this case, right? Because you're not ranking based on any predicate. So the items are fairly good. All of these are indeed cables that would satisfy my query. Now I'm going to scroll down so that we can look at the results that were discarded by DataSift. So here you can see an item with DataSift rank -1. This is, in fact, a mini B cable. It is not a printer cable. This is a scanner PC interface cable, which I don't know what that is. Then there's a micro cable. Then there's a printer, which is not even a cable. And the further down you go, the more strange the results get. Right? They're not even cables, beyond a point. All right. So once again, DataSift does a fairly good job even for this query. To summarize, DataSift is a toolkit for efficiently executing gather, filter, rank workflows on any corpus. There are lots and lots of applications of DataSift. How do you help school teachers find appropriate articles to assign to students? How do you help shoppers find desired products? How do you help journalists find supporting data or supporting images? Right? And there are lots of challenges in building DataSift. How do you make it flexible and extensible? How do you optimize the individual operators of gather, filter, and rank? And how do you optimize across the entire workflow, which is something we haven't yet addressed. So I won't have the time to get into the detailed design of DataSift. I'm going to talk to you about just the optimization of just one of the operators, specifically the filter operator. All right. At this point, are there any questions? Yes.
Yeah, just the 2 examples you just mentioned, right? So,
yeah.
For example, how do I find the right reading materials for students? With image recognition, that's something anyone can do. So people can look at an image and say that's a student. finding out what is an appropriate book for a classroom is something that almost no one can do if you pick up sort of random people off the internet. So is that really an adequate task here?
True. So okay. So it is true that in some cases, if the material is too specialized, it might not be appropriate to use a general purpose crowd. But the thing that I had in mind, the use case that I had in mind was a little more simple. Let's say I want to assign articles on global warming, and I want articles that are well written, that have, let's say, neither a liberal bias nor a conservative bias. It sort of considers, I don't know, it sort of has a very neutral bias. It considers the pros and cons of both arguments. And it is from a reputable source, right? So these are things that anyone can check, I think. Anyone who has English background. Of course, if it's a very detailed technical, I can't, for instance, use DataSift to ask for related work to my publication, right? That's something that I can't use it as of now. But I suspect once we have a better sense for skilled workers or skill sets of workers, I think we can get there eventually, but not right now. Any other questions? Yeah.
So why did you divide your task into gather, filter? So what's the model? I thought you were going to describe a system which does more general purpose querying, but you're choosing this particular division called gather, filter, rank, that covers your examples.
Right. So I will talk about another system briefly which does general purpose computation. But this was a specific enough task. Even though this is very specific, there are lots and lots of applications that fit under this model, so it merited like detailed investigation. And the so one aspect that is different, although the other system does have filter and rank components, it does not have a gather component. The gather component is very new to this system. So I don't think there are corresponding components in the other system. But I'll get to that later. Yeah.
A related question is, if you look at databases, there are relational algebra operators.
Yes.
So these look sort of analogous to those relational algebra operators.
Precisely.
Do you have a language, or because typically the interface to a database is a language, and
yes,
everything is implemented using composing operators. Mm-hmm. So these are the operators you use to compose. Or is there a language interface? Or
no, in this case, this is the interface. It's only gather, a sequence of filters, and a rank step. That is the restricted language that I can handle. But our toolkit is flexible enough that you can plug and play these operators if you really want to, but we are not supporting queries.
Your interface is almost like the relational algebra.
But only for filtering and ranking. That's it. No like complex operations like...
These are your set of operators.
Yeah, these are the set of operators.
Well, the gather is like the from clause, isn't it?
Yes.
In a sense, yeah. Right.
One thing that strikes me as very interesting about all of this is, I mean, do you sort of envision a kind of a marketplace of, I mean, in some sense, both gather and filter, depending on how specialized the question is, you might be willing to pay more to get people with different levels. It's almost like a matchmaking service between people who have specialized kinds of knowledge and people who have questions that need answering.
Absolutely. Yeah, so I see this as just the first steps towards a very specialized marketplace where most of the people who are currently sort of going to day jobs are, and this is certainly happening, a lot more people are looking for employment online, and this is certainly transition to skilled labor of the kinds like programming, design, virtual assistants. All of this has already moved a lot to these crowdsourcing marketplaces. Not enough to replace existing companies, but people really like this service, right? I mean, they can. It's a flexi time. Flexi cost. They can choose whichever project they are interested in. It's great. And I think there will be a need in the future to optimize the use of these humans even for skilled labor. And that's precisely the point.
The ultimate outsourcing.
Yeah. Yeah. Yep.
It's scary.
Depends on who you are.
We're giving opportunities to everyone, right? Anyway, that's a perspective I take. All right, so let me move on to filtering. Filtering is an algorithm that forms part of the core of the applications that I just mentioned, as well as the other application that I will talk about later. It's also one of the fundamental data processing algorithms. So in filtering, you have a data set of items. I don't need to tell you this, but you have a data set of items. You have a predicate, and you want to find all the items that satisfy the predicate. Right? So in our case, items could be images. The Boolean predicate could be, is this image a cat? And I may want to find all the cat images in this data set. Right?
The Boolean predicate is in English. The NLP is in English sentence.
Yeah, it's an English sentence, much like the predicates that I had earlier. Yeah. So this is not something I can automatically evaluate. That's the key. So since I can't automatically evaluate, I need to ask humans, right? Does an item satisfy this predicate or not? And since humans may make mistakes, I may need to ask multiple humans. So the question is, how many humans should I ask? When should I ask them? How should I ask them? These are the kinds of questions that come up in this part of the talk. Yes.
With the data set, is it something, the data set can be the web itself, right?
Sure, but in my scenario, I have a restricted data set. So the way to think about this is, let's say I did an initial gather step. I have a set of images that I consider as.
Because what I'm asking is certain queries, you may be able to optimize the gather step.
Yeah.
Is this image a cat? If you could just do a Google or Bing image search on cat,
Yeah.
you'll already get a bunch of, so some parts of predicates in your task, you can probably push to the gather phase if you're working off a live feed in the search engine or something.
So are you suggesting that I move? So I think what you're mentioning is the option of moving some of the predicates from the filter step to the gather step.
No, so
Is that-
so you're doing crowdsourcing.
Yes.
And you're probably the questions you're interested in addressing are fairly general.
Right.
So what I'm trying to understand is it always in a set of pre-computed items, or the most general source is the web itself, right? So if you think of the source as the web,
Yeah.
and you have some predicates in mind, let's say you have 5 predicates.
Mm-hmm.
Some of those could be pushed to simple search predicates, which will already filter the images from the web.
Okay.
And it's sort of optimizing inlining some of the filtering with the gathering.
I think what Ravi
So in some sense, I mean, you gather already has a filtering operation there, right?
Yes.
Exactly, yeah.
So gather, filter, rank,
Sure.
that is not completely disjoint in some sense.
I agree.
Right.
I agree, and that is one of the reasons why we haven't been able to optimize the entire workflow yet. I'm just talking about this one individual operator and trying to optimize that. There are very complex interactions between gathering and filtering and ranking, in the sense that one of the versions of the system that we are building involves gathering keyword query suggestions from the crowd, retrieving a few items for each of those query suggestions, then filtering them, and then going back to the gather step to gather even more for the keyword query suggestions that did well.
So let me try to rephrase the question in a different way.
Yeah.
As a user of the system, my view is that, like Ravi said, the data set of items is the web.
Mm-hmm.
There are all these images on the web. I want to know what are the images of a cat.
Yeah.
I can think of it in 2 ways, right? The data, I just post this query to the DataSift system. The DataSift system breaks it down into a gather phase,
Yeah.
because it can't handle millions of images. It has to come down to thousands of images.
Okay.
So it extracts something from my filter and poses a query to the web and gets something
Yeah.
just as a first set,
Yeah.
as a candidate set, and
Yep.
then issues the queries to the users.
Right.
Or I could have a different view of the system where the onus is on me to come up with that.
Who is you?
I'm the user of DataSift.
Okay.
The user of DataSift, the onus is on the user of DataSift to come up with a gather predicate.
Okay.
So how is it? The onus is on the user, right? DataSift doesn't automatically extract the predicate for the gather phase.
It could be, so the toolkit is general enough that it could have both options. So one option is, okay, so let me go back to DataSift, right?
If I just mention nothing in gather and just say search using Google Images and just put filter predicates, what happens?
Say that again?
My gather phase, the gather phase, the phase is empty.
The topic is empty.
Empty. You just search all Google Images. That's
Right.
implicit meaning, right?
Right.
And then I say image of a cat.
Right.
What will happen?
So as a filtering predicate. So in this case, so there are different versions of the system. One version of the system takes the entire query and asks the crowd for keyword query suggestions.
We'll ask the crowd for
Keyword query suggestions. So that will be used in the gather step to retrieve initial items. Then you will filter those items based on the
So there the DataSift system is automatically figuring out what keyword.
Right. Of course, if I use the current, the version that uses the topic to ask keyword query suggestions, that's obviously not going to work in this case, right? Yeah.
So just to sort of try to put this in a perspective that I can understand, one way to think about the gather step is maybe you give something crude as a way to specify what the set is. And then the filtering predicates are actually a validation stage.
Exactly. Yes, perfect.
So gather step also has a ranking, right? For example, I want cat.
Yes.
Now in the Google image,
Yes.
there are say 10,000. But
Yes.
this system can support only 1,000, right?
Yes.
So how do you even decide like how many to start in the gather phase?
Great question. So while we've not yet done anything sophisticated in that step, all that we do is take the top 10 results, multiply it by a factor k, and then retrieve those many results and then process it. That's all that we've done so far. So there are many ways of thinking about this question. One is that the search results are somewhat correlated with the final results, right? So beyond a point, going down the search query the search results is not a good idea, right? If you're searching, for instance, for let's say I don't know, clip art of students studying, beyond the 1,000th image, you're not going to get students studying at all. You're going to get very noisy images.
Here you're making some assumption about the data source, that Google image is doing a good job.
I am making some assumption about the data source. I agree.
But shouldn't that initial set, the size of that initial set that you say, okay, so you should query for Google images, you get 3 million of them.
Yes.
You have a budget of $5, so shouldn't you use that budget as a guide? Well, so how big should my initial set be?
Certainly.
Restrict that 5 million down
Certainly.
to 20.
Certainly.
Because that's all you can afford to ask.
Yeah, so that is something we haven't yet done, right? The entire workflow optimization is something we haven't yet done. So right now I have some ad hoc rules that govern how many items, how I use my budget I mean, I have a rule that says gather so many items for how many items I actually need. But that is a great point, yes. Overall, that's what I need to do. I need to think about how much I'm spending in the gather step, how much I'm going to spend in the filter step. And the set of items constantly shrinks as you go from the gather step to the filter step to the rank, right? So I need to think about how much I'm spending in each of these steps. It's a very complex problem. And hopefully, by just talking about filtering itself, I'll convince you that it's complex enough. All right? So shall I get into filtering?
Yes.
All great questions. Please keep asking. All right. So, and in this part of the talk, I'll focus on the trade-off between quality and cost. I will not consider latency, although we also have results for that case. And for now, I will assume that all humans have the same error rate. This is another assumption. This is an assumption I'll get rid of later on in the talk. All right? So how do we filter? Well, we use a strategy. So this is how we visualize strategies in a two-dimensional grid. The number of no answers gotten so far for an item along the y-axis, the number of yes answers gotten so far for an item along the x-axis. At all yellow points, we continue asking questions. At all blue points, we stop and return that the item has passed the filter. At all the red points, we stop and return that the item has failed the filter. Okay? So this is just one example of a strategy. Let me emphasize that. An item will begin at the origin. Let's say we ask a question to a human. We get a no answer. The item moves up. We ask an additional question. We get a yes answer. Item moves to the right. We ask an additional question. We get a no answer. Item moves up. And let's say I get a sequence of yes answers. We stop and return that the item has passed the filter. All right? So the key insight here is that since I'm making the assumption that all workers are alike, the way I get to a point is not as important as the fact as I'm there, right? So these strategies are Markovian. And for those of you who are familiar with stochastic control, this is in fact an instance of a Markov decision process. So this might be familiar to some of you. Right? So this is just one example of a strategy. Here are other strategies. Always ask 5 questions and then take the majority. Right? Wait until you have 3 yes answers or 3 no answers, and until then keep asking questions. Right? So other examples of strategies. Now let me move on to the optimization problem. So in the optimization problem, this is one of many variants. I'm given or I estimate via sampling using a gold standard if I have one, or I can approximately estimate it if I don't. The per question human error probability. So this is a probability that a human answers yes, given that an item does not satisfy the filter, and the probability that a human answers no, given that an item satisfies the filter. And I also know the a priori probability of an item satisfying or not satisfying the filter, right? So I know these quantities. Huh?
How do you know the a priori probabilities?
So if I have a gold standard, then it's easy in the sense that assuming the gold standard is a sample of the actual data set, then it would be an accurate estimation. The fraction of true yeses versus true nos would be the estimate of the a priori probability.
Probability is a probability that any arbitrary image is an image of a cat.
Exactly. So in the DataSift case, I estimate these quantities approximately as part of the processing. So since it's a completely unsupervised system, I actually estimate these quantities while doing processing. So I do a little bit of sampling, approximate sampling to estimate these quantities.
How sensitive are the results to how well you do on those?
I haven't really checked, so I don't know how sensitive it is. But my understanding is that these strategies are fairly robust. So even if the estimates are off, and we've done this using synthetic experiments, even if the strategies are slightly off, you still get fairly good results. Yes?
Have you done anything on, sorry, have you done anything on trying to filter out, what should I call them, sloppy users or malicious users? Somebody who just clicks no on every image or yes on every image?
Yeah, so there is...
Recognize that.
Yeah.
Or you could also seed something, seed the input set with things that you know are correct.
True.
Right?
Yes, perfect. So in the DataSift case, it's completely unsupervised, so I can't do this apart from sort of using the other workers, other humans' estimates to check if a given human is good or not, right? That is disagreement-based scheme. We also have work on dealing with data quality, but it's not integrated into this current system. So right now, the way I think about it, in this part of the talk, I'm assuming that all humans are alike. And since Mechanical Turk is such a, rapidly varying pool of people, that's an accurate assumption to make because I don't have the reliable error rate estimates for people over time. Because the pool of people that I have access to rapidly changes. So at any given time, I won't have a worker who I've seen before.
So does Mechanical Turk maintains the accuracy of those users? Or
No. So all that they maintain is the number of tasks that these users have attempted in the past and their approval rate. And the approval rate is not of any good because if you do not approve their work, then all the workers will boycott you. So you just approve their work, typically. That's just a factor. That's just something you do. Right? So Mechanical Turk does not have a good reputation system. All right. So quality is an important aspect. Right now, we are sidestepping quality by assuming that all workers are alike. That's one. The other, we do take into account if we have estimates of worker quality, that can be taken into account while filtering by suitably downvoting, in some sense, the bad workers. And I will tell you about that later on.
Maybe you can take the users to the workers to some tests to make sure that they are of some decent quality.
Great. Yes, that is an option that is often used in practice. Unfortunately, in DataSift, because the task is new, every time a user uses my system, I'm getting a completely new task. So testing the user on something I have information about earlier is not going to help.
But you can probably use the results from previous tasks and give it to your system to sort of judge the quality of previous workers.
But
so they will be the new sets.
But But I mean, suppose you're doing this task for thousands of things.
Yes.
Someone can just do 10 of those, and those 10 could be a test. Even that would be good enough probably to
Guys, we can generate lots and lots of ideas here.
Yeah, all good ideas, but yeah.
Why don't we let you continue? That's what you actually did.
All right, thank you. Yeah, and my goal is to find the strategy with minimum possible expected cost. In this case, since I'm paying the same amount for every question, the expected cost is nothing but the expected number of questions. And I want my expected error to be less than a threshold. So this is the second objective. The last constraint is that I want my strategies to be bounded. So I don't want to spend too much money on any single item. So what the last constraint means is that the strategies fit within the two axes and x plus y is equal to m. Okay, so I don't spend more than, say, 20 questions on any single item, which is reasonable. All right, so how do I estimate expected cost and error? So given a strategy, the overall expected cost of a strategy is nothing but summed over the red and blue points x comma y, x plus y, which is a proxy for the cost, times the probability of reaching x comma y. All right? And overall expected error is the probability of reaching a red point and the item satisfying the filter, plus the probability of reaching a blue point and the item not satisfying the filter. So these are the two ways you can go wrong, right? And how do I compute these probabilities? Well, I can compute it iteratively, right? So the probability of reaching this point is the probability of reaching this point and getting a yes answer, plus the probability of reaching this point and getting a no answer, right? So I can compute these probabilities iteratively. So I now have a way of computing expected cost and error of any strategy. So here's a naive approach to compute the best strategy. For all strategies, evaluate cost and error. And yes?
I have a clarificatory question. Is this problem identical to the problem of estimating a bias of a coin, or is it different? People have studied estimating the bias of a coin through sampling, right?
No, so I assume that I have my estimates already.
No, each picture is a coin.
Okay.
Each picture has a probability of satisfying your requirements or not.
No, in my case, I know the true. I know that each picture is either a 0 or a 1. I'm not given that each picture is a probability. It's not a bias. Each picture is a 0 or a 1. Given that an item is a 0 or a 1, I have probabilities of getting wrong answers. Okay, so naive approach for all strategies that fit within the two axes and x plus y is equal to m, evaluate expected cost and error, and return the best one. How do I compute all strategies? That's easy. For each grid point, you can assign it one of 3 colors, red, yellow, and blue. Run through all possible strategies and give the best one, right? Of course, this is exponential in the number of grid points. If you have 20 grid points, or anyway, so if you have 20 grid points, the order of 3 to the 20, and in other cases, it gets even worse. So this is exponential in the number of grid points, so this is not an approach we would like to take. Right, so I've given you a naive approach to find the best strategy, and I'll call these deterministic strategies for reasons that will become clear shortly. Computing the best strategy is simply not feasible. It takes too long, but the resulting strategy is fairly good. It has low monetary cost. I have another algorithm that also gives me a deterministic strategy. Once again, this is exponential, but it's feasible. I'm able to execute it for fairly large m. The resulting strategy is slightly worse. It has slightly higher monetary cost. But I'm not going to talk about this algorithm either. I'm going to tell you about a different algorithm. In order to do that, I need to introduce a new kind of strategy. As some of you may have guessed, the new strategy is a probabilistic strategy. So in addition to having yellow, blue, and red points, I have points that are probabilistic. So with like this point. So with probability 0.2, you continue asking questions. With probability 0.8, you stop and return that the item has passed the filter. With probability 0, you return that the item has failed the filter. All right? So these are probabilistic strategies. We have an algorithm that gives us the best probabilistic strategy in polynomial time. And since probabilistic strategies are a generalization of deterministic strategies, this is in fact the best strategy, period. Okay? And we can get that in polynomial time. Since this is the best strategy, it has the lowest possible monetary cost. So over the next 4 slides, I'm going to give you the key insight behind this algorithm and then tell you about the algorithm. Okay, so the key insight necessary is the insight of path conservation. So you have, for every point, a fractional number of paths reaching that point. And what that point does is to split the paths. Some of the paths continue onward, some of the paths you stop and return that the item either passes or fails the filter. So pictorially, let's say there are 2 paths coming into this point. This point decides to split the paths 50-50. So one path continues onward to ask, one path you decide to stop. For the path that continues onward to ask, asking an additional question, this path moves to the point above as well as to the point on the right. Okay, so this is how path conservation works for a single point. Now, how does path conservation work for strategies? You have one path coming into the origin. Since it's a continue point, it lets the paths continue onward. So one path goes to this point and to this point. Once again, since it's a continue point, it lets the paths flow onward. While this is a probabilistic point, let's say the probability is 50-50. So half a path flows onward from here. So overall, you have one path ending here, 1.5 ending here, and half a path ending there. All right, so this is how path conservation works in strategies. So now, finding the optimal strategy is easy. We simply use linear programming on the number of paths. And so you have a number of paths coming into each point. Those are the variables. The only decision that needs to be made at each point is how these variables are split. Everything else is a constant multiple. So the probability of reaching a point is a constant times the number of paths reaching that point. The probability of reaching a point and the item satisfying the filter is a different constant times the number of paths. And returning pass or fail at a point does not depend on the number of paths. All right? So finding the optimal strategy for this scenario is easy. You just use linear programming. Now, I'm sure you thought of many issues with the current simple model. We have generalizations that can hopefully handle all the issues that you've thought of. All right? So let me pick a few of them to explain further. All right, so the first generalization is that of multiple answers. So instead of having a Boolean predicate, yes, no, what if we want to categorize an image as either being a dog image, a pig image, or a cat image? Or you want to rate an item as being either 0 out of 5, 1 out of 5, all the way until 5 out of 5. In this case, we simply record the state as the number of answers of each category that I've gotten so far. Once again, I can use path conservation and linear programming to find the best strategy. Second generalization is multiple filters. So far we considered a single filter. What if we have a Boolean combination of multiple independent filters, like in my DataSift example? In this case, we simply record the state as the number of yes and no answers for each of those filters. And at any point, you can choose to ask any one of those filters, or you can stop and return that the Boolean predicate is either satisfied or not satisfied. Then the last generalization is that of difficulty. So far, we assumed that all items are equally easy or equally difficult. So they all have the same error rates. What if they are not, right? What if there is a hidden element of difficulty? We capture that using a latent difficulty variable. And the error rate of each item is dependent on that latent difficulty variable. Once again, we can capture that in our current setup. Now, let me move on to a harder generalization. So this is a generalization of worker abilities. So let's say I have 3 items whose actual scores are 0, 1, and 0. Worker 1, who's a very good worker, decides to answer 0, 1, and 0 for these 3 items. Worker 2 decides to answer 1, 1, and 1 for each of the 3 items. So he's a fairly poor worker. Worker 3 is adversarial, so he flips a bit for each of the items. Right? So he's a fairly bad worker, but he gives us a lot of useful information. We can just flip his bit. Anyway, so how do we handle such a case? We are losing a lot of key information by assuming that all workers are alike. So we can reuse the trick from multiple filters. We can certainly record the number of yes and no answers corresponding to each of the workers, and this certainly works. Unfortunately, if we have many workers with varying abilities, we have an exponential number of grid points, right? And therefore, our approach does not scale. All right, so over the next 3 or 4 slides, I'm going to tell you about a new representation that helps us solve this problem. Any questions at this point? All right. So instead of recording the number of yes answers and the number of no answers gotten so far, we record the posterior probability of an item satisfying the filter given the answers that you've seen so far along the y-axis and the cost that you've spent so far along the x-axis. Okay? So now to make it clearer, I'm going to map the points from the previous representation to the new representation. So the point at the origin maps precisely to the a priori probability of an item satisfying the filter, and cost is equal to 0. All right? These 2 points map to points above and below that point at cost is equal to 1. Right? And the remaining points would map to their respective points in the new representation. Now, as an approximation, I'm going to discretize the posterior probability of an item satisfying the filter given the current answers into one of a small number of buckets. And as a result, multiple points in the old representation may map to the same point in the new representation. Right? Notice that I can discretize it as finely as I want, right? As finely as my application needs. So if we have many workers with varying abilities, we can once again map this 2n dimensional representation to that 2-dimensional representation. And as an interesting property, as we reduce the size of the discretization, make it smaller and smaller, the optimal strategy in the new representation tends to the optimal strategy in the old, more expensive representation. All right? So what changes in the new representation? Well, instead of starting at the origin, you now start at the a priori probability of an item satisfying the filter with one path entering the strategy at that point. If you have all workers having the same error rates, you have 2 possible transitions, one above and one below, all on spending one unit of cost. So you always transition to the right. If you have n workers with varying abilities, you have order of n transitions. So the size of each linear equation scales up by order of n. And once again, everything else works. You can use the path conservation property and linear programming to find the optimal strategy. So let me quickly tell you about one more generalization that works well in the new representation, then I'll move on to experiments. So the other generalization that works well in the new representation is the generalization of a priori scores. So what if I have a machine learning algorithm that provides for every item a probability estimate of that item satisfying the filter? For instance, I may have a dog classifier, and the probability estimate may be proportional to the distance from the classifier as well as which side of the classifier the item lies. This is easy to use as part of my strategy computation. Let's say I have 50% of items with probability 0.6 and 50% of items with probability 0.4. I simply start half a path at 0.6 and half a path at 0.4, and the strategy computation proceeds as before. When running a strategy on an item, the item will begin at its a priori score. And this a priori score sort of would capture the intuition when we have already have the input data set having a ranked list of results, right? That could it could certainly help in that case as well. All right, so told you about a number of generalizations. We have other generalizations that I did not have time to cover. Yes?
Yeah, so I have like one question of the problem formulations.
Mm-hmm.
So in this case, you studied the filter operator.
Yep.
But in practice, I would argue for your application, a much more natural operator is I have some 1,000 images, and I want to pick 50 images from cats, right? If my ultimate goal is to pick 50 images from cat, it may not be optimal for me to consider each image and get it graded, right? It's much better for me to consider an image, and if an image is marked yes, I want to prefer those images. But if an image is starting to have some variation, like variance in the marking, so it's probably not useful because I want to focus on images which are more limited. So it seems that the nature of the problem will fundamentally change if you incorporate order.
Certainly.
And
so that's another problem we've studied. And the key insight in that scenario, when you want a fixed number of items from a data set that satisfy the predicate, is that as soon as an item falls below the average item in the data set, you would rather pick the average item in the data set. That's the intuition that you had as well. Right? And we have a separate paper on that. I'm not going to be focusing on that in this talk. This, in addition to systems like DataSift, also appears in lots of natural scenarios. Things like companies do this all the time. So things like content moderation, right? A lot of companies have a content moderation phase before they upload the image. The user uploaded images go on the live site. They have a content moderation phase where they use crowdsourcing services. In that case, you need to go and manually check every single image. Right? And the second application that I'm going to tell you about, also you need to go and manually inspect every single item. All right, so, but yeah, so the finding k items that satisfy the predicate, that's a natural algorithm that we've studied. Yeah. Okay, so I'm going to now tell you about experiments. I'll use that as an excuse to tell you about the second application that we've been studying, that is MOOCs. So I'm sure you've heard of MOOCs, massive open online courses. They're very trendy. There's in fact even a Photoshop poster of the movie The Blob, which has been photoshopped to read the MOOC, which I thought was quite cute. MOOCs are revolutionizing the world of education. There are hundreds and hundreds of courses, each being taken by thousands and thousands of students, right? There are lots of courses that require subjective evaluation, courses like psychology, sociology, literature, HCI, and so on. And there's no way TAs can go and evaluate all the assignments in all of these courses. So what we need, therefore, is peer evaluation. So peer evaluation is crowdsourcing, but with an important twist. The important twist is that the evaluators are also the people being evaluated, right? Okay, so now the key question is, how do you assign evaluations for submissions so that you can accurately determine the actual grade of each submission? And notice these were the images that DataSift gave me for my initial example. Okay, so deciding whether or not to get additional evaluations for each submission is a generalization of filtering that I considered, where I want to rate an item as being either 0 out of 5, 1 out of 5, all the way until 5 out of 5. So we are very lucky to have the data set from one of the early MOOCs offered at Stanford. This is the Stanford HCI course. In this case, you have 1,500 students with 5 assignments, each having 5 parts. These are graded by random peers whose error rates we know, because we've had them go and evaluate assignments for which we know the true grade. Okay, so we know their error rates. And our goal is to study how much we can reduce error for fixed cost or vice versa. So here is one sample result. I'm plotting the average error. In this case, the average error is the average distance from the actual grade. And remember, actual grades are between 0 to 5. And along the x-axis, I have the cost. In this case, the cost is the average number of evaluations for each submission. And I'm plotting 3 separate algorithms. The first is the median algorithm that requests a fixed number of evaluations for each submission and then takes a median. The one-class algorithm that assumes that all workers are alike, have the same error rates, and uses the old representation. And the two-class algorithm that puts workers into 2 buckets based on their variance, high variance and low variance workers, and uses a new representation, right? So for now, let me focus on the median algorithm and evaluations equals 5. So in that case, the median algorithm has an error of 0.3. So this is in fact the heuristic that is currently being used in the Coursera system for a range of courses like psychology, sociology, and so on. So we can get to the same error using just 60% of the cost using the one-class algorithm and just 40% of the cost using the two-class algorithm. From the perspective of error, if I fix the cost at 3, I can reduce the cost, the error by 40% if I use the one-class algorithm, and by 60% if I use the two-class algorithm. So either way, I can significantly reduce both cost and error using our strategies. All right? So here is, at this point, I'm happy to take questions because this is, all right, moving on. So let me tell you about other work in the crowdsourcing space that I've worked on, other research that I've done, and then conclude by talking about open problems. Yes?
So in terms of filtering, so if you have multiple filters, like in your data, example you showed like 4 or 5 filters,
right.
So how do you handle them? Do you ask separate questions for each of them, or
yes.
do you...
Yeah, so currently the way we handle them in the filtering operator is by having a separate question for each of those filters.
Okay, but you could also consider kind of combinations. And
true. The reason why we decided to go with separate questions for each of the filters is because it's not very clear. Humans are more likely to make mistakes with a combined question because it's not clear what question they are answering. If it is a single unit question, it's much more clear what they are answering. If it is it's like, does it satisfy this and this and this and this, they might say no, even though if it does satisfy, or the other way around. But yeah, good point. Okay, so we've studied other aspects of data processing in addition to filtering, finding the best item out of a set of items, categorizing an item into a taxonomy of concepts, identifying a good classifier for imbalanced data sets, also the search problem, which is the one that you mentioned, the finding key items that satisfy a predicate, determining the optimal set of questions to ask humans. In a lot of these cases is NP hard, even for very simple error models. Therefore, we need to resort to approximation algorithms. And recently, we've started looking into some of the data quality issues as well, which are common to all of these algorithms. Let me move on to Deco. So DataSift is, in my mind, an information retrieval-like system powered by the crowd. Deco, on the other hand, is a database system that's powered by the crowd. Right? So I don't need to tell you this, but database systems are very good at answering declarative queries over stored relational data. But what if the data is missing? What if I don't have the data? So Deco can actually tap into the tiny databases that exist in people's heads. So it can answer declarative queries over stored relational data as well as data computed on the fly by the crowd. So if you ask a query like this, asking for the cuisine of Bytes Cafe at Stanford, Deco will gather the fact that the cuisine of Bytes is French and return that as a result for the query. Right? So, yeah.
This system works perfectly, it is subsume gather. What?
Not the gather step.
I thought this system is about gathering.
It is gathering missing data. It's not the keyword query suggestions. I mean, it would take a lot of sort of mangling DataSift, mangling Deco to fit under DataSift. But it is true that this is a much more general purpose system than DataSift. All right. So here are key elements of Deco's design. It has a principled and general data model and query language. You have user configurable fetch rules for gathering data from the crowd. This is sort of like access methods, if you will. User configurable resolution rules for removing mistakes or resolving inconsistencies from data gathered by the crowd. One such resolution rule could be the filter operator. Right? We need to, due to the three-way trade-off between latency, cost, and quality, we need to completely revisit query processing and optimization in this scenario. So we have a working prototype which was developed by a colleague and myself at Stanford. You can pose, and there's also a web interface. So Deco supports, the prototype supports Deco's query language, a data model, query processing, as well as optimization. There's a web interface where you can pose queries, visualize query plans, and get results. Right? So let me move on to data extraction. Let's say I have a website like Amazon, and I want to extract an attribute like price from all the web pages on Amazon. I can ask humans to provide pointers to where the attribute is present on a given web page. Then I can extract from all the pages on that site. Right? But what if the web page is modified? So my pointers are no longer valid, and I may end up extracting incorrect information. Like in this case, I may end up extracting the fact that the Kindle costs $10, right? So what do I do in such a case? We built a robust wrapper toolkit that can reverse engineer where the pointers have gone in the modified versions of the website. So you can continue to extract from modified pages accurately, right? So you can significantly reduce the cost of having humans provide pointers once again. So our robust wrapper toolkit had some very nice theoretical guarantees, and over an internship, I deployed this in Yahoo's internal information extraction pipeline. Okay, so there's lots of related work that we build on in the crowdsourcing space, work on workflows, games, and apps. Whenever I give talks, I typically get questions on the first 4 topics. Although my work is more similar to the last 2 topics, Deco and DataSift are similar to the recent work happening around the same time on CrowdDB and Quark. And parallelly, there's been a development of a number of other algorithms, sorts and joins, clustering, and so on. Okay. Now let me tell you about some of the other research I've done. I've also worked on course recommendations for a course recommendation site called CourseRank. Course recommendations pose a number of interesting and challenging aspects. So you need to deal with things like temporality, because courses are typically taken in sequence. You need to deal with requirements, because courses need to be recommended that are not just interesting, but also help the student meet graduation requirements. Right? My course recommendation engine had some nice theoretical guarantees, and this was deployed into CourseRank. CourseRank was spun off as a startup by these 4 undergrads and deployed at about 500 universities. And I think a year ago it was purchased by a company called Check.com. All right, so
you don't need a job, right?
There's this T-shirt, right, that says, all I got was, my friends had a startup, and all I got were the lousy research papers, right? Yeah, so I've worked on human-powered data management and recommendation systems. In addition, I've also worked on information extraction and search, but I won't have time to cover that in this talk. So in all of my work, I've followed a sort of end-to-end approach to research. I model scenarios conceptually, starting from simple error models and then generalizing, like in the filtering case. I formulate optimization questions that make sense in the real world. I find optimized solutions using techniques from optimization, inference, approximation algorithms, and so on. And I build systems with these solutions, right? Systems like DataSift, Deco, the robust wrapper toolkit, and so on. Of course, in research, it's never really a linear path. There are lots and lots of iterations. But I intend to continue using this end-to-end approach in research. Right? So I think human-powered data management is only going to get more and more important in the future. There are more and more people looking for employment online. And so there's a need to manage and optimize the interaction of this giant pool of people who are interacting online in a seamless manner. Right? And of course, more and more data is being accumulated. However, many fundamental issues in crowdsourcing remain. Issues like it takes too long, sometimes the work is badly specified, sometimes workers are error-prone, sometimes humans don't like the tasks that we give them, and sometimes it costs too much. Okay? So I have initial angles of attack for all of these issues. Let me pick a few of them to explain further. So latency can be addressed by having systems produce partial results as they do their computation. But this requires revisiting the computation models of systems and algorithms. Given two algorithms, how do we pick the one that produces interesting partial results faster? Right? So to deal with poorly specified work, how can we use a crowd to decompose? So one more point about the eager computation. This is related to some work, prior work in the database community on online aggregation, for instance. To deal with poorly specified work, how can we use a crowd to decompose a query to a workflow? What should the intermediate representation be? How can we verify the correctness of this intermediate representation? To deal with error-prone workers, how can we monitor their performance to see that their performance doesn't start to drop? How can we be sure that our estimates of their performance is correct? And how and when should we provide feedback to workers that they're doing a good job or a bad job? Right? So the steps that I'm arguing for go beyond looking at systems and algorithms to the other steps in the pipeline, the interaction with humans, as well as the interaction with platforms. So once we solve some of the fundamental issues in crowdsourcing, I think there's no end to what we can do. There are many, many hard data management challenges that could benefit by plugging in humans as a component. And of course, designing some of these systems would bring about a whole range of additional challenges as well. For instance, how can we impact interactive analytics using humans, right? Can humans help formulate queries? Can humans help visualize query results? How can we build better consumer-facing applications powered by humans? By combining human and computer expertise, can I build a newspaper, a personalized newspaper that beats Google News, for instance, right? Can I build human-powered recommendation systems? How can I impact data integration, a problem database people have been working on for decades now using humans? Overall, I think there are lots of interesting problems in redesigning data management systems by combining the best of humans and algorithms. At this point, I'd like to mention that a lot of the work that I've done in my PhD is in collaboration with a number of collaborators both at Stanford and outside Stanford. In particular, I'd like to call out my advisor, Hector Garcia Molina, my unofficial co-advisor, Jennifer Widom, as well as frequent collaborator, Alkis Polizordis. Right? At this point, I'm happy to take questions. Huh? You guys are there. You guys are there.
Akash and Jeff.
Huh?
Who is the collaborator between Akash and Jeff?
Akash and that is Ming Han. I couldn't find a photo of him.
You collaborate with humans and not humans.
Huh?
You collaborate with humans and sometimes non-humans.
Yeah, I should have mentioned the crowd of Mechanical Turk workers. That was a mistake. Yeah. Any other questions? All right. Thank you so much for attending.